the light so blue and depressing?
Why is it so blue and depressing?
Yeah, that one, the one under Connor's like cold.
It's because it's Connor. Okay, so I heard a couple good things. Can anybody tell me what is the area under this curve going to be equal to? Not 2. What is the area going to be equal to, Caleb? It is going to be equal to -2. When we have area under the curve and it's in the negative region, we have to say it is a negative area. Okay? It's a little bit hard to understand that because technically that isn't real. Negative area is not real. Unfortunately, in calculus, we do reference it quite a bit. If you think about it, remember how we talked about the area under the curve being the distance you walked in a velocity thing? Well, if I walk this way, I'm going in a positive speed, right? So I go 10 feet this way. But let's say then I walk backwards, negative. What do I have to do now? I have to take that 10 feet and subtract however much I walked backwards. That is what this is referencing. Okay? So now let's go ahead and look at this. What about from 0 to 2 pi? So everybody go ahead and graph from 0 to 2 pi again, like so. What is the area under the curve here?
Is it just 0?
It would be just 0. The area under the curve here is just 0 because, well, we have 2 here, -2 here. You add the areas, what do you get? 0. So 2 minus 2 equals 0. How about for 0 to pi over 2? Let's go ahead and graph this out again. This is pi. Pi. Where would pi be? Sorry, pi over 2 be? In the middle on the first. Right here.
Probably gonna be
So, what is the area here? It is going to be 1. Very nice. Okay. All right. So, pretty simple and common to see. This is how we do the areas under the curve a lot of the times. You'll be given like an answer, and then you just have to use that part and what you know about sine graphs. Oh, look. Here for sine graphs, we know that because this is positive, this is negative, and these should be the same. They'll cancel. If we know this area, we know this area. And then if we know this area, well, we know that this side is going to be symmetrical. It just goes up to the top, highest point, and then goes down the other way. These values are matching as we go along. We know that this is equal to this, that to that, that to that, and it kind of progressively goes down. Therefore, splitting that in half, splitting the graph in half, should split the area in half. Yes?
Can you explain how you got 2 here from number 2 minus 2?
This one? What's the area of from here to here? I give it to you at the beginning. Remember? What's the sine of x dx from 0 to pi? All the way up here? 2. So that's the area under that part. So that's equal to 2, 2, 2. So that's 2, that's -2, which is 0. Okay? Now, what happens if we do 2 plus sine of x dx? Okay, well, let's see what happens. Let's graph this out. If I add 2 to sine of x, what does that do to the graph?
Moves it up.
It moves it up by 2. So right here, I'm going to go 1
Oh, yeah, way more areas.
and 2, and then 3. This right here is now our x-axis. Whenever you have a vertical transformation of a trigonometric function, all you need to do is graph the graph at whatever your vertical changes. So instead, we're going to treat this as if it was the x-axis. So I'm going to go here, start here, go up, down, here. So from 0 to pi, what is this area going to be equal to? Well, let's check this out. This right here is going to be pi one is interesting. It's a little bit harder.
Is it 4?
They just do.
0 to pi.
Ah. 2 times.
Go.
So plus 2 pi.
Anybody have an answer they'd like to share? Answer they'd like to share. Cody?
2 plus 2 pi.
2 plus 2 pi. Very nice. We know that this is going to be 2 plus 2 pi. I had the wrong answer. I was looking at my answer and I wrote 6 there for some reason. Like, how did I get 6 from that? So here this would be 2, because that is the area of this curve here. Then what do we have to do? We have to do the area of this down here. And what is the area of that's not a square, that's a rectangle. The area of that rectangle there is going to be the height times the width, so plus 2 times pi. Or if you want to call it like 8.14159, something else, you can also call it that. Okay. So let's go ahead and do the next one then. What happens if we multiply it on the outside? 2 times the sine of x dx. Graph it out. I'm actually going to go here and just graph half of it right now. Like so. So this would be 1. This is going to be 2. All the way up here.
Yeah.
It is a stretch, correct. What do we think that area is going to be? Cody?
4.
It is going to be equal to 4. Very nice. Now this one is interesting. We haven't talked too much about this. But remember, if it's on the outside, if I add or subtract a number on the outside, is a vertical translation. But if I add it on the inside of the graph, on the inside of the function, what does that become? Not vertical, but horizontal. And remember, horizontal is always opposite. If we have a minus, it's actually a to the right. It's a plus. So let's go ahead and jot this out. We have this graph here. And we're going to basically move this over 1, 2. And then this here is actually going to be 2, so, or pi plus 2. Has anything actually changed in this graph when we start here and graph it this way? How much did we move here? We went from 2 to pi plus 2. So what's the difference in between these two? Pi. So wait, and isn't that just going to be the same as all of this in the beginning? So what would the answer to number 6 be?
2.
It's just going to be 2, right? So a horizontal translation, as long as you also horizontally translate your interval, is not actually going to change anything. Okay? Okay. Let's look at, how about sine u du? Does changing x to u actually do anything? No. It's just a different way to write it. So here we have the integral there. So I'm going to go ahead and graph this one out. This one you have to graph the left and the right. So we go from here to here. From here to here. Okay. This one, I heard some people already talk about it a little interestingly. I will tell you right now, the x values don't matter if they're positive or negative. We treat those as width no matter what. So if I have this -2 over here, I'm not going to treat that as a -2 because what's the distance from here to here?
2.
No, sorry, what's the distance? Sorry. The distance from here to here is just, if this is negative pi, what's the distance here? So how long is this? pi length.
So it's-
So it's not negative pi length because we can just flip it away and look at, oh, it's pi length.
But
Okay?
it's negative times negative.
That's why it's so just, for the x's, you just don't. Okay? So what is the answer to this one going to be? It's going to be 0. Okay? How about from 0 to 2 pi of sine of x over 2? Well, ooh, this one's a little harder. I want to see if anyone remembers, how do you graph sine of x over 2? This is going to be a stretch. Because remember, in horizontal, everything's opposite. Dividing by a number will make it bigger. Because what it's saying is it's going to take twice as long, right? Before it's twice as fast. So if you go twice as fast, is that longer or shorter? It's shorter. But if you go twice as long, it's going to be longer. Okay? So your graph is going to look like this. From 0 to 2 pi.
Is it a vertical stretch?
Usually it looked like this. No, it's a horizontal.
It's a horizontal.
Horizontal stretch. That's the normal. This is what it looks like now. We're only going to have half of that.
Let me guess.
So what's the area under here going to equal?
5.
What do we think? I have some correct answers.
4.
The answer is 4. Sine of x over 2 dx is equal to 4. I know, but then I heard like 7 more answers. and I'm
Because
like,
you didn't respond.
what? I was giving everyone a second to think.
Okay.
Jeez, Caleb.
Sorry.
I think you need to move on. You need to move up, yeah. You kind of do
Oh, for sure.
Oh, for sure. Yeah, let's just send you straight to BC.
BC.
Well, you remember, BC is this class, just
This is true.
5 times faster.
I'm basically Connor in it.
Yep. So when you all take BC next year, you will learn almost the exact same stuff, take a lot of the same notes, but you'll be doing harder problems and going faster and faster. Yep,
Yeah.
because that's what you do in calculus. You relearn.
First semester AB and then the second semester like you learn new stuff.
C.
No, it's kind of like the first semester. I think you get through one more booklet. So basically, you'd be doing this booklet in the first semester, and then you'd be doing other booklets, and then you try to get to the new booklets that you haven't done yet, because we're just not going to get to the end. Because remember, AB is like this, BC is like this. So you need to go all the way through here, speed through it, and then get to this part that you don't actually have in BC and AB. So from 0 to pi, cosine x dx. Remember, cosine x dx is just going to be a horizontal translation of sine of x. So it is going to look like this. We're going to start at 1. We're going to go here, here, and stop. So what is the area of this graph here?
Oh, it's about 0.
It is going to be equal to 0. If you want to continue to graph it out, it looks like this. So this is only half of the graph. And notice we have this area here, this area here. These two, because of the same reason I was talking about the sign before, are going to be equal to the same thing. Now, go ahead and answer question 10 real fast. Suppose that k is any positive number. Make a conjecture about negative k to k, the integral from negative k to k of sine of x dx, and support your conjecture. K is any number. So input any number. Negative 1, 2, 8, 7, whatever you want.
Uh-oh.
Yep, very nice. Support it though. So I try to remember, because whenever you answer these questions on like tests and stuff, you always have to actually answer why. So try to answer why that would be true. So you should be writing a couple sentences at least, maybe 1 or 2. So how does that happen? Like, how do you know, how does that happen for sine? Because it doesn't happen for cosine, it happens for sine. Just try to think of a way to explain it. I want to hear these explanations as well. So I see that a lot of people have the correct answer. Does anybody have a good explanation that they want to put forth? Good explanation they want to put forth. Alice?
It's because like it's the exact same number except one's just negative, so when it goes to 0.
So I don't understand that. So you have to explain it in a, so you mean for this here? But is that going to be true? So why is that true for sine though?
Because it passes through 0 as well. So like it's an even amount.
Okay, so you're correct there. I would need a little bit more because I would need to ask questions to get there. Someone want to expand on that? What do we know about the right side and the left side of sine of x? There are reflections across the what? Reflections across the origin, right? If you reflect this across the origin, what does it turn into?
Oh.
This right here. So therefore, if they're reflected across the origin, then going anytime this way, like Alice said, and going anytime this way, it doesn't matter how far you go, as long as you stop at the correct points in the positive and negatives, they will have the exact same area under them, and they will always cancel each other out. Okay? Yes?
So, that's called an odd function, right? So do you have to like write odd in the explanation, or?
You don't have to write an odd function, no. You could use that. That would be good if you remember that and be like, because sine of x is an odd function, and by definition, an odd function is reflected across the origin. So therefore, that is kind of expanding on that. That it's good. I like that. Yes, Emma?
For cosine, is it like would that still work technically because it's a reflection across the
No, it
y-axis, or just?
It would not, because if you look at cosine here, like so, if we go from pi over 2, this is negative pi over 2 to pi over 2, do these areas cancel?
No, because they're both positive.
They're both positive. But then if you look here, the only reason they canceled before is because of this, right? So therefore, no, because this is not an odd function, it's an even function, right? And even functions are going to have a reflection across the origin, and therefore they are not going to have that same property of, oh, this will cancel with that. This would need to be down here in order for that to cancel. It's not always going to be true. Sine is just special that way. It's a very special trigonometric function. Okay? Now, let's go down to the next page. So flip over to the next page. This is kind of bringing it back to discontinuities. We talked about how in order for us to integrate something, it has to be continuous. However, there are kind of steps that we can take in order to do this. In order to actually be able to take the area, we just have to we have to use our imagination. And imagine that some things aren't real, and we could just kind of like push things away. So, explain why the function f of x equals x squared minus 4 over x minus 2 is not continuous on 0, 3. Anyone tell me why it's discontinuous? Catherine?
Because at 2, if you plug into it for x on the bottom,
Very good. At x equals 2, we have a discontinuity. At x equals 2, 0 in denominator. Now, what type of discontinuity is this? Is it an infinite, is it a jump, or is it a removable? Remember the difference between infinite and removable, though. Yes, babe?
is it removable?
It is removable. Why is it removable?
Because you can cancel with the difference of squares on top.
Very good. If you all look at this up here, right, we get x squared minus 4. How can I factor x squared minus 4? That becomes x plus 2x minus 2. So parentheses, x plus 2, parentheses, x minus 2. All over x minus 2. And what graph are we left with? What is the end behavior of this function going to be? This is going to be equal to x plus 2. So therefore, if you graph this in your graphing calculator, it will look a lot like just x plus 2. There might be a little bit of weird stuff happening around the value of 2. But the way we can graph this is we can graph it just as this graph, right? but with some removable discontinuity. So let's go ahead and try that out. So this is what the graph would look like. You can graph this one if you want, but you don't have to graph this one. We're not going to use this one. So let's we go here, 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 and here, here, here. We're going to start at 2, then we go up 2 over 1, and then we're going to go up to 2. However, what happens is we kind of go like this. Straight down. So here, there. And then at 2, we have this little strange thing. It's not an asymptote necessarily. It's we will get really close to it whenever we touch it, but it just becomes awkward again. Then we have this here, where we have the next point. It jumps up here and continues along. And if you look, this is the graph of y equals x plus 2. The more you zoom out, the more it will just look like y equals x plus 2. So let's go ahead and just actually graph out, well, what can we use instead? We can use x plus 2. So this is 0, 1, 2, and 3. And we want to show that if we take the integral, or if we find the area of x squared minus 4 over x minus 2 from 0 to 3, it's going to equal 10.5. So let's go ahead and do this. We have here, we're going to start at 2. Right here. Up 1 over 1. Up 1 over 1. But I'm not going to put a dot there. What should I put? I should put a open circle. Right here. So I'm going to put an open circle right there to show that, okay, that is a removable point. Then I'm going to go up 1 over 1 again. Up to here, and this right here is my graph. Now, there are a couple different ways you can do this. It's kind of up to you how you want to do it. But remember from the proficiency check yesterday, go ahead and make a shape. You can make a trapezoid, you can make a rectangle, you can make some other rectangles, and then try to find other areas under there. I want to see what y'all do to try to determine that it is 10.5. I like to always draw this down here, like so. So connect that down there. And you see kind of what shape it is. There you go. We need a triangle and rectangle. Right. There you go. Very nice. Okay. We're using MRAM.
Oh, no, I already did it. I'm just experimenting.
Oh, okay. It's not that problem. I'm going to actually use, I know it sounds crazy to do this, I'm going to use the trapezoidal equation for area. Do we all remember the trapezoid equation? We take the height of the trapezoid, which is going to be the two, which is going to be whatever the distance between the two different bases are. Remember, the two bases have to be parallel in a trapezoid. So I'm going to take this right here. I know that my height is going to be 3 times, and then I add my two bases and average them out. I'm going to do the average of 2 plus 3. Oh, sorry, no. 2 plus 5 divided by 2, which equals 3 times 7 over 2 equals 21 over 2, which is equal to 10.5. Or you could have just done this right here. The area of this is 6. The area of this is 5. That's 3. 5 times 3 divided by 2. 15 divided by 2. Wait, whoa. Oh, sorry. Thank you. The height is 3. Because we have to do this here. This is the height of this is 2. This is what some other people did on the PC yesterday. where they said, they made the same mistake I just did, where they said, oh, the height from here to here is 5. It's not. It's whatever x, this y value is, and you have to take away the 2. It's easy to forget, exactly. So then the area here, that's 10.5. This is going to be 5 times, this is going to be, what was it? 3 times 3, which is 9 halves. 9 halves plus 6 is 10.5. Okay. Now, do we all remember int functions? Does anyone remember? Oh, sorry, Catherine. Yes.
So how did she go from the first graph to the second graph?
Because it is a removable discontinuity. We cannot do this with others. If we ever have something like, well, what about 1 over x? Could we ever do this with 1 over x? No, we cannot, because can we remove this discontinuity? Yes or no? No. However, using the fact that x squared minus 4 over x minus 2, we do have some cancellation that happens there. All we know is, well, the graph looks like this. What's the end behavior? What does the graph really look like? It looks like x plus 2. But what can we never have in the graph? 2. So that's why we have to cancel that out. It's a little confusing at first, but just know you can integrate with removable discontinuities by using this form of integration.
But how is it removable? The first graph is going to negative 8 and then coming.
Have you tried graphing it in your calculator? Go ahead and look at it. That's why I said this is a bad representation. That's why I didn't want y'all to write this out. This is kind of how you would draw it out a little bit when you do it. However, it looks pretty funky when you do graphics. Everybody else, go ahead and try to do the last one. Draw out an axis, and try to graph the function of int x. Remember, that's integers. Do you remember how to graph integers? Do you remember this graph right here?
Oh, golly. Barely.
See if we can graph that one. Remember that one?
No.
Okay.
What are the lines?
It's the int graph. So what does it look like? Because that is actually what happens. Because what happens when you input a this is kind of what happens as you actually, so if you zoom in further and further, if you try to zoom in really, really close,
Go to
it will
math,
start to look a
and
little
then number, it's
zoom,
math
zoom,
number 5.
Zoom in. You know this.
What do you mean?
So our last year, right?
Looks like
Kind of show this a little bit.
From 0 to 1, it's just at 0. And then from 1 to 2.
So you'd have to go, it's a little bit hard to see.
It's 1.
Oh, so I was wondering.
Here, I'll graph it. It should look like that.
It's the closest, it's the integer that it's, yeah. So it's the integer
Where
that.
every y value is just like this. Oh, I see a connection.
Oh, aren't these just like straight up boxes?
Wait a second.
If you think you have it correct, go ahead and look up at my graph.
Wait, can we use our purple?
It's the latest.
Well, that's because it's.
You don't need to use LRAM or MRAM.
Oh, I just found a connection.
Oh, okay.
Yeah,
Oh,
I
was
did
it
it before
connection?
that. Well, it just looks like the LRAM graph.
Oh, yeah, it does. It does. Mm-hmm. The nice thing about this is that LRAM, MRAM, and RRAM are all going to be,
Equal.
it should be equal, right? Because the leftmost point here is going to be the same as the rightmost point here. Here's the same thing. Leftmost point, rightmost point. Leftmost point, rightmost point. Middle point, same thing. Okay? So, how do we do this? What is the area of the first rectangle here? The area of this is going to be 1. The next area is 3, 4. 1 plus 2 plus 3 plus 4 magically becomes 10. Hooray! Okay. Now, just so you all know, we're in a little bit of an awkward spot for tomorrow because a lot of you are just going to be missing for the history star exam that you have to take. So if you're a junior, sucks to suck. Sorry about that. Seniors, you do not have to do anything. You can come to class and all that. So tomorrow's going to be a work day for us in calculus. I was gonna have it be a work day anyway, so we can answer questions and stuff. But for today, your homework is going to be 7 through 14. That is for tonight. And then 15 through 24 is what we're working on in class tomorrow, all of those. However, if you are a junior, 15 through 24 odds, try those problems out. You don't have to do every single one of them, but you need to try those out. Okay? Is there no 24? How many are there? 21. 15 through 21. Sorry. Well, actually, no, 6 more problems isn't going to be bad.
No, I want to do the odds.
And then I might have like a little activity or worksheet for us to do tomorrow, but it might just be kind of more of a chill day instruction time for us. We can play countdown. All right, go ahead and get to work. Yes, we good?
How do we graph this?
In your calculator.
I would just do x plus 7 and then count the window.
Ooh, this is fun.
Okay. Graph the
Oh, and everybody, so for those who aren't going to be here tomorrow, I was going to talk about this more tomorrow. Everyone, click math, and then 9. Math 9. So go back. So go back to your. So go back to like your regular. Back to, so you know what that means?
Nah.
You just put it in there.
Oh, and then you can just graph it.
You don't have to graph it. You can just put that in. That gives you the answer.
Can we just do that on like any?
You can, however, I'm gonna limit you because I need to see graphs and stuff, because there are gonna be times where you're not allowed to use your calculator on the quizzes, like on the AP exam. So you need to know how to do it by graphing under the graph, and then other ways later on. So I'm showing you this because some of them you will need it for, and it's good to check your answers and see, okay, well, what happened, what did I do wrong, things like that. But NINT is what you need to do. Math 9 is NINT. It means definite integral. Right?